Okay, so this is the displacement current as the voltage in the capacitor is changing at that rate. Okay, but remember, the capacitance for a parallel plate capacitor is epsilon naught A by D. Did I get all the factors right? So voltage is. Okay, let me start off again. Del del T and so JD is that. Epsilon naught. Okay. And displacement current is JD times area equal to epsilon naught area divided by D del V by del T. And this was the capacitance of the capacitor for a parallel plate capacitor. So for a parallel plate capacitor, the displacement current is the capacitance del V by del T. Okay. So here's a parallel plate capacitor. The potential difference between parallel plates shown above is instantaneously increasing at the rate of 10 to the power 7 volts per second. So this term is 10 to the power 7 volts per second. What is the displacement current between the plates? If the separation of the plate is 1 centimeter and has an area of 0.2 meters squared. Okay. So the displacement current is given by the capacitance del V by del T. And this is a parallel plate capacitor. The capacitance is epsilon naught area by D. Okay. So this is given, and that's given. So the displacement current is epsilon naught is 8.85 into 10 to the minus 12. Units are Coulomb squared, Newton meter squared. Area is 0.2 meters. D is 1 centimeter, 10 to the minus 2 meters. And del V by del T is 10 to the 7 volts per second. Okay, that's 10 to the minus 10, 10 to the minus 3. Okay, so displacement current is 10 to the minus 3, and this will be in amps, 8.85 into 0.2. Okay. So that's 0.88, so 176, 177, 1.77. So 1.77 milliamps. And you guys measured a current like that the other day, yesterday. Yeah. This says if electric and magnetic field strengths vary sinusoidally, sinusoidally in time at frequency 1 gigahertz, being 0 at t equal to 0, and that when are the field strength next equal to 0? So I'll draw the electric field. Okay, so if it's 0 there, it's 0 at half the period. Okay, so electric field is 0 at t equal to 0, and then at the next time it's 0, it's at half the period. Okay, and period is related to the frequency like that. So it'll be 0 at t equal to t by 2, which is equal to 1 over 2f. Gigahertz is 10 to the 9 a second. So 0.5 into 10 to the minus 9. So half a nanoseconds later. And by the way, the period is 1 over f equal to the period is a nanosecond. When do they reach their most negative values? This is half a period. This is 3/2 of a 3/4 of a period. So it'll reach then. Okay, so t equal to 3t to the power 4. It reaches its most negative value at 3/4 of period. .75 nanoseconds. And how much time is needed for one complete cycle period? Okay, one complete cycle happens at t equal to t equal to 1 nanosecond. A radio station broadcasts at a frequency of 760 kilohertz. So that was in the notes. At a receiver some distance from the antenna. The maximum, at some distance from the antenna, the maximum magnetic field of the electromagnetic wave detected is 2.15 times 10 to the minus 11 Tesla. The Earth's magnetic field is 10 to the minus 5 Tesla. So this is 1,000,000 times weaker than that, the magnetic field. Okay. All right, so if you're receiving a electromagnetic wave from Orlando, Orlando is in that direction, the electric field is coming like this, the magnetic field is coming like that. So if you want to catch the electromagnetic wave, if you're using rabbit ears, if you're using a dipole antenna, you want the dipole antenna to be like that. And that electric field is making a current in this dipole antenna. If you want to detect the magnetic field, I don't know if you guys remember, back in the old days, you had ring antennas. And the rings are detecting the changing magnetic field. That's inducing the, okay. What's the problem with that? So, what's the problem with the ring antenna? If you want to detect Orlando, the ring has to be the plane of the ring has to point to Orlando. If it's like that, your signal strength is weaker. Okay. But with the antenna like that, you don't care if you're detecting Orlando or Melbourne. This can point like that. So with the ring antenna, if you want to detect Orlando, you got to point like this. And if you want to detect Melbourne, you got to turn it like that. Okay. So you can detect the electric field or magnetic fields. Okay. But with magnetic fields, when you're detecting magnetic fields, you have to orient your antenna properly. Anyway, so a radio station broadcasts at a frequency of that. Let me show you that antenna. See, here's those ring antennas. Those are the rings that sense magnetic fields. So here's a ring antenna that you don't have to change directions. You just have multiple rings. So here's the ring antenna. Here's the ring antenna. All right, what is the maximum electric field strength? Okay, so E max or B max, you want to see, so so 6.45 times 10 to the minus 3 volts per meter. Millivolts per meter. So if you have an antenna that is 1 meter long, when that wave goes by, it's inducing a millivolt in the antenna. Okay, so that electric field is inducing a millivolt in that antenna. That's what that means. What is the wavelength of the wave, electromagnetic wave? So B. And the wave frequency is 760 kilohertz. And so we'll make this 10 to the 6, so 300 divided by 0.76. meters. So the wavelength is roughly from here to Mainland High School. Almost like, yeah. At what distance does a 100-watt light bulb produce the same intensity of light as a 75-watt light bulb? Okay, so 7,500. Okay, so the intensity of light, it's the power of the bulb divided by the area over which it's spread. What is the area of a basketball? 4 pi r squared. Okay, so you want the same intensity here and there. Okay, so what you want is power, the 75-watt power, 4 pi r 75 square equal power of the 100-watt bulb. So you can okay, so this is the intensity, but also you can think of the, so if this was a radio station and you're transmitting at low power, that is the coverage you're getting. And if you transmit at a higher power radio station, you're getting a larger area of coverage. Why would you want to do a larger area?
More listeners.
More advertisers. Okay. So, but this costs you more money. And if you make enough money, then it's worth it transmitting at a higher power. Okay? More listeners. All right, so R100 over R75 equal to P100 or P75 per half. So So we're doing it at 10 meters away, I guess. So R100 is 10. So what this equation is telling you is a 100-watt bulb will give you the same intensity as a 75-watt bulb, 15% more distant, further away. So if this was 10 meters, it'll give it the same intensity at 11.5 meters. Okay? If this was 100 meters, it would give you the same intensity at 115 meters. So 15 meters away. That's what that equation is telling me. A small helium neon laser has a, so helium neon lasers emit red light, so those laser pointers that you see with the red light, that's, well, those are, a lot of them are solid state. But anyway, a small helium neon laser has a power output of 2.5 milliwatts. What is the electromagnetic energy in a 1 meter length of the beam? Okay, so this is emitting 2.5 milliwatts. Milliwatts is millijoules per second. And in 1 second, the beam length is c. Okay? So if you're standing here, in 1 second, 2.5 millijoules will pass you, and the length is c. Okay, so the energy content in 1 meter is 2.5 millijoules divided by c meters. Okay, because this is how much energy passes you in 1 second, and the length that passes you is c meters. So it's 2.5 millijoules divided by 3 times 10 to the 8 meters. No, well, not meters, we'll just divide by. So the energy is 2. So what we're saying is, when you shine this laser, you guys have seen that the red laser, and in that laser beam, and that most people use for talks, a meter of that beam contains this much energy, 3 trillionth of a joule. Why do you care about this kind of calculations?
Does it tell you how long your battery lasts?
Yeah, but anybody have had LASIK surgery? Huh? Okay, so in a LASIK surgery, what they do is, so here's your eyeball, they cut your cornea, peel it back, and they burn cells with lasers. They got to precisely control the energy deposited. So that tells you how many cells you burn off. So you need calculations like this then. Huh? Yeah.
You did the same exact calculation,
Mm-hmm.
but it looks like you got a different answer. You got 8.33 times 10 to the negative 12, and
Yeah.
it looks like you solved for U instead of E, or maybe V.
All right. 25 divided by 3 is 8. Nobody was paying attention. 8.33. And I wasn't paying attention because I was thinking about the story I wanted to tell you. I got to think 3 steps ahead. So anyway, and I mean, if you're wanting to shoot a tank and kill a tank, you know how much energy you need to deposit and stuff like that. So at top of the Earth's atmosphere, the time average Poynting vector associated with sunlight has a magnitude of 1400 watts per meter square. Remember, I was telling you the intensity of sunlight. What are the maximum values of the electric field? So the intensity about the Earth's surface, about the Earth's atmosphere is 1400. Intensity is 1400 watts per meter square. Okay, and you saw that the intensity, which is the average Poynting vector, is equal to E max B max by 2 mu naught. Okay. That's I'll point out. There is the formula. So on the formula sheet, I've copied this entire thing and posted that. So you have to. What is it that they're asking you? What is the maximum values of the electric and magnetic field? So magnetic field is B max, and then EB is related like that. So B max will be E over C. So intensity is E max square over 2 mu naught C. So this is the amplitude of the electric field in sunlight, okay, in space at Earth distance. Only half the sunlight reaches the surface of the Earth. Okay? Half of it gets reflected and scattered from clouds and all. Mu naught is 4 pi into 10 to the minus 7. And C is 3 times 10 to the 8. And this will come out in volts per meter. So let's take care of powers of 10. That's 10 to the 1. We'll borrow 10 to the 3 there. 10 to the 4 to the power half is 10 squared. And what you're left with is 1.4 So that's the strength of the electric field that's the amplitude of the electric field in sunlight. Okay. Of course, this is a rough calculation. Sunlight is composed of all kinds of different wavelengths, and if you chose a given wavelength for a given wavelength, that's not the intensity. So this is assuming it was a monochromatic light, but we won't worry about that. Now we'll find out. This is an interesting problem. What is the total power radiated by the sun? Okay. And assume the distance is that. So here is the sun. we know the intensity at Earth, the power, intensity is power over 4 pi r squared. That's the surface area. Okay. So power is intensity times 4 pi r squared. Intensity at Earth is 1400 watts per meter square. 4 pi, and the distance to the Earth is 1.5 times 10 to the 11 meters. So let's do this. That's 10 to the 3, 10 to the 22, that's 10 to the 25 watts. 1.4 times 4 pi times 1.5 squared. So here's, so the power of the sun is, that's a 100-watt bulb. 4 trillion 100-watt bulbs. No, 4, this is trillion. 4 trillion 100-watt bulbs. And that's how much, how, the sun, that's the power of the sun. A 2.5 diameter university communication satellite. So there's a dish out there next to the building. That's we don't use it anymore, but anyway, so communication satellite dish receives TV signals that have a maximum electric field strength. Maybe we do. For one channel of the electric field strength is so the and E max equal to 7.5 microvolt per meter. And remember, the intensity is related to E max square, like so, 2 mu naught C. What is the intensity of this wave there? So the intensity of the wave is 7.5 into 10 to the minus 6 volt per meter square, 2 mu naught into 10. Okay, that's 10 to the minus 12, and then minus 7, so that's 10 to the minus 5, and then minus 8, that's 13, 10 to the minus 13. Intensity is watt per meter square. And that's 7.5 square divided by 6 times 4 pi. this is pretty amazing. So, you know, the intensity is 10 to the minus 15 watts per meter squared, 75 times that. Or, yeah. So, if you think of a 100-watt bulb, a 100-watt bulb light shining on this thing, all you have to have is 1,000 trillionth of a 100-watt bulb shining on this. And you can sense that signal and get information out of it. If the orbiting satellite broadcasts uniformly over an area of that, how much power does it radiate? Okay, so that is the intensity you're getting at ground level. And okay, so you're getting from the satellite. And the area covered is 1.5 times 10 to the 13 meters square area. So power radiated is intensity times area. We just calculated the intensities. 75 times 10 to the minus 15 watts per meter square. And the area over which it's radiated is 1.5 times 10 to the 13 meters squared. So 7.75 times 10 to the minus 2 watts. 0.75 watts. Only 1 watt. That's all it does to radiate. So if your if your instrumentation is dish, okay, so the electronics, so what you're getting is the power, this is per meter square. Your dish is 2.5 meters diameter. So pi times that is pi, 2.5 square, okay, so. Okay, so intensity is that, and if you multiply the intensity times the area of the dish, the power to the antenna is 5 times, what did I do? Okay, 5 times that, over 5. Okay, 400 times 10 to the minus 15 watts. That is the power you're feeding to your electronics. Okay, this guy gathers light and it feeds to the electronics that much power. And you're able to operate. So more sensitive your instrument, the less power the satellite has to emit. Okay. And why is that important? Because the satellite is, where is it getting power from? Solar panels and stuff like that. Yeah. Yep.
Is it 75 times 1.5 and 12?
I'm sorry?
For the power?
That's 10 to the minus 2.
And that's 75 times 1.5.
Yeah,
Oh.
the final power is 1.12.
Yes, so 75 times that is roughly, let's say, 150. 75 times 1.5. I don't know where I am today. So the power is 1 watt. Pretty neat. Okay, I'll do that. Problem will take a little too long. We'll do this one. What is the frequency of a 193 nanometer UV radiation used in laser eye surgery? So they use a UV light, okay? And you'll see in a second why they use that. What is the frequency? Oh. Okay, so the wavelength is 193 nanometers. That's 193 times 10 to the minus 9 meters. That's the wavelength. 0.193 into 10 minus 6 meters. Okay, so the smaller the wavelength they use of light, the smaller the area you can burn. And roughly this is the size of a cell, so you can burn roughly 1/10 the area of the bell. Okay, so that's why you use smaller and smaller wavelengths. Okay, so the burn can be more precise. Okay. And higher frequencies, shorter wavelengths have more energy as well. So let's So there's the frequency of the light. So this says, part B says, assuming the accuracy with which this electromagnetic radiation can ablate, reshape the cornea is directly proportional to the wavelengths. So the smallest burn you can make is roughly equal to the wavelength. So the shorter the wavelength you make, the shorter the spot you can burn. You're reshaping the cornea. How much more accurate can this UV radiation be than the shortest visible wavelength? The shortest visible wavelength is 400 nanometers. That is blue light. And you're using 200 nanometers, 193 nanometers. So you're twice more accurate. Okay. All right.